Every week, we've been gathering together with really phenomenal people from around the world and getting a glimpse into their lives and the things that they do, bringing you some really interesting science and curiosity at home. So my name is Jasmine. I'm with the Telespark team, and thank you for taking some time after your lunch today to join us. I just want to mention before we welcome our guest, which by the way, hello, Nathalie.
Hi.
That normally we do these lives on Wednesdays. And yesterday you would notice that we pushed this live to today. And there was a really important reason for that. And it's because yesterday there was a shared mandate and movement called Shut Down STEM, which asked those of us in the science outreach community, science centers, academia, and others as a community to just take pause for a day and ask ourselves, what are we doing? And what are we reflecting on? And what are we acting on to create impact, but as well as to build action towards inclusivity and equity in the world of science. And so we took a day at Telespark to do that as a team, even though we're all really working remotely right now as a science center awaits to reopen and welcome you all back. But that's because we are members of a community, and you at home are members of a community. And so I just want to thank everyone for joining us today as we pulled a little very important switcheroo. So today is an Ask Me Anything, and today we are joined with an incredibly special guest. Everyone and their dog is interested and just astonished by space. The universe around us and grounding us here on our own really beautiful blue planet. And so we're welcomed today by Nathalie Ouellette. Nathalie, welcome, and thank you so much for joining us all the way from Montreal.
Thanks for having me.
Of course. So Nathalie, you are the outreach scientist for the James Webb Space Telescope, which what a remarkable initiative, but also what a remarkable job. I think that, we often joke here in Alberta that if you grow up on the prairies, you want to be a marine biologist because we're surrounded by grass and not water. But at the same time, too, I think everyone at some point in their life goes to that moment of saying, I would wish I could be an astronaut, or I wish I could be, an astronomer. And you've made a career out of exploring the universe. I just love if you could tell the audience a little bit about who you are, your background, and how this came to be, because what a cool job.
Sure. And I actually never thought of this before, but you mentioning living in the prairies away from the water and dreaming of being a marine biologist. I grew up in Montreal where we have a lot of light pollution, and I didn't get a lot of really beautiful nighttime sky views. But the few times that I went out in the country and I did see the stars in the Milky Way were really impactful. So maybe there is a little bit of a connection because I didn't have it on a daily basis. I grew to appreciate it even more. So I have a few pictures that I can share to talk a little bit about my background. So as I mentioned, Montreal, not great for stargazing, but every once in a while I would go in the country and then I would look at the stars and I would be really, really fascinated by them. And I was lucky because I grew up in a household with two scientists, two engineers as parents. So, and that was really good too, because I saw both a male role model and a female role model who had the same job. So they were both engineers. My dad tested materials. He's retired now. And my mom builds planes, and she still builds planes now. And she actually now works for the company, Northrop Grumman, who is building the James Webb Space Observatory, Space Telescope. So we have
this is really a family affair. That's remarkable.
Yeah. So I grew up with science around me. And from a really young age, you can see me here with my mom. I'm about maybe 5 years old here. I really, really became obsessed with nature, but not just any kind of nature, when nature was really powerful. Yeah. So I became obsessed with reading about natural disasters. And so I love tornadoes are my favorite, but I love volcanoes too. I know you have a session coming up on volcanoes. Oh, and then when I tried to figure out what is the most powerful thing in the universe, it's something huge, on a galactic scale. So this is where I fell in love with galaxies, and I decided to become an astronomer. And I did lots of schooling, but like lots of interesting schooling. I got my PhD in 2016 working on galaxies, galaxy evolution. And during that time, I wasn't always only at school. I got to travel to all these kinds of amazing places like New Mexico, Hawaii, Chile, to work at these telescopes. So that was really, really fantastic, a great opportunity. And I haven't regretted it one single moment.
How fantastic. And so, literally looking up at the universe and saying that this is my incredibly vast area of study seems huge. I just want to ask you, because you shared the fact that your parents are both come from scientific fields, and so that was at home. But was there aspects of curiosity or no limitations? Like, what do you think it is about maybe what you were taught about how to explore that maybe helped guide you through this to the scale that you've been able to achieve?
Well, definitely both my parents really encouraged being curious in general. They really wanted me to ask questions about everything that was around me. And when they saw that I was interested in that specific topic, they would encourage me to like follow through. I had a phase, everyone had a phase like this, but I had a long phase being obsessed with dinosaurs. And I was like a teenager during part of that phase too. And I remember my father, I was saying, oh, maybe I should start finding a job this summer, like trying to get a little bit more money in the bank. And he was like, I would rather you like read up on dinosaurs and like explore that and try to figure out like what you want to do long term. So my parents really encouraged my scientific curiosity in general, and helped me, they rented documentaries for me, and they bought me a telescope, and they brought me to the library. I spent so many weekends at the library with my mom. So they really encouraged that curiosity in me.
I think that's really beautiful. And, curiosity and maintaining a healthy dose of curiosity at all ages is a really powerful thing. And I think right now, as many of us are still at home and we're just starting to open up our social circles, I know that Calgary, where Telespark is located, and Montreal, where you're located, are in different phases. But being curious, whether we're inside our homes or out exploring the world or out exploring the universe, is really important. And so for those of you at home right now, I want you to kind of like get that curiosity and start like evoking it outwards. So in the chat, if you have any questions that are space related or Natalie's career related, just interested in how galaxies are formed, is there life on other planets, etc., pop those questions in. And as Nathalie and I talk, and as we learn a little bit more about some of the projects and niches that she's on right now, we'll get to those. And so I really encourage you to take a moment and send those in. And so Nathalie, your curiosity led you to the footsteps of the James Webb Observatory, and now you're actually the science outreach for the James Webb Space Telescope project, which is a massive and incredibly exciting project. Can you share what that is with us?
Sure. So I feel so happy and grateful to have this position, not only to be on this mission, but also to be the bridge between the scientists working on it and the public. So it's a huge mission led by NASA, but with really important contributions from the European Space Agency, but also the Canadian Space Agency. And a lot of people know about the Hubble Space Telescope and all the wonderful things it's done. It just celebrated its 30th anniversary, and it's still going strong, but it is getting older. And what's a lot of people might not know is that Canada didn't have a stake in the Hubble Space Telescope, but we are involved in the James Webb Space Telescope. So it's going to be not the replacement, but the successor, because we're hoping that they actually overlap a little bit. And it is a really gorgeous telescope, very different. Hubble, if you've seen it, is like a big silver aluminum cylinder, essentially. But James Webb is an open telescope. The mirror is out in the open. It's made up of hexagons. It's so beautiful. You can actually turn it into a piece of jewelry, as you can see. On my necklace here. And it's plated in gold because the type of light that it is interested in studying, infrared light, which is different from visible light, is reflected more effectively with gold. Whereas a more silvery material like aluminum for Hubble is really good for visible light, the light that humans can see. So it has a very, very unique look. And you can see in this image here all the little people that are crowded around it. So it is big. It is 6.5 meters wide, very, very big. And here it's going through some tests. So they had to build this like huge vacuum chamber that they shoved the whole thing in to like simulate the conditions of space to try to make sure that it can survive its launch into space. And launching it, oh, go ahead.
Have you been in that room? Have you been one of the people in the full outfit that's had a chance to see this beauty up close?
I have been, so there's like a viewing bay where you can like look into the clean room. I've been in the viewing bay to look into like where the telescope is. So I've seen it with my own eyes through a window, but it's very, very few people get to actually go there, because anytime you build something that goes up into space, it has to be in what we call a clean room with clean suits, or bunny suits is another name that we call it, because we have to make sure that there is no dust on any of the components, because that can really mess up the electronics. So it's very controlled, but I've been able to come relatively up close to the space telescope.
Wonderful. It's as close as you can get.
Exactly. So one thing that's really exciting about it is how complex the deployment is. So I have a little animation that I'll play in the background here. So Hubble had a super interesting story, because when it was launched, it got launched into what we call low Earth orbit. So just a few hundred kilometers above our heads. But there was a problem with its mirror at the very start, and it required astronauts to come to the rescue and sort of fix the mirror, and it solved all the issues. But it could only be placed close to the Earth because the Earth itself doesn't glow very brightly in the type of light that Hubble was interested in. But the Earth and the moon both glow very brightly in infrared light, just like humans glow really brightly in infrared light, which is why when you put on an infrared camera, you start seeing like humans glow. So we need to send this thing 1.5 million kilometers away from the Earth, which means if something goes wrong, we can't fix it, unfortunately. So that's a really interesting part of this. And also because it's so big, even one of the largest rockets that we have, the Ariane 5, we can't put the telescope in it sort of like as it would be in space. It needs to be folded up on itself like origami. So when we launch it, it's going to be in its folded up configuration. And as it's hurtling through space towards its final destination, it will start unfolding. So this is what you see here, the deployment sequence. So a very nerve-wracking time. It's going to take 14 days for it to unfold completely. So we will all be sleepless and terrified here, making sure that everything goes well.
It's phenomenal. And what a brilliant feat of engineering and collaboration. And so I believe Maria in the comments here first asked for a little bit of an understanding between the difference of the Hubble and of course of the James Webb Space Telescope. And I think you've done a fantastic job of sharing that with us. But she's also wondering, do you work for NASA? And I think that's a valid question, considering there's a lot of parties that come together. What about collaboration makes this stuff possible, and who are the parties involved?
Yeah, so I don't work for NASA, but I work with NASA. And I don't even work for the Canadian Space Agency. I work with the Canadian Space Agency. So these missions are so complex. Over the lifetime of the mission, probably upwards of 10,000 people have worked on this project. It's been going on for several decades now. I'm still relatively new. I've only been working on it for a few years. And so I work with the Canadian Space Agency, who is one of the main partners in the mission. NASA leads the mission, but one of the contributions that the Canadian Space Agency has given to this project is an instrument. So there are several instruments that go into the telescope, 4 scientific instruments, and one of them is the Canadian one is like a 2-for-1 special. It's called FGS and NIRIS. FGS is what we call the fine guidance sensor, and it's basically a camera that it counters the fact that the telescope is always sort of vibrating a little bit. And so we want to take really, really clear images. That camera allows for all the images taken by the telescope to be super crisp and clear. So it's like a mission critical instrument that if it doesn't work, the whole mission doesn't work. So Canada, super important in the mission.
Yeah, we can't spend this many decades and deploy that and have blurry images. So
exactly.
It's a Canadian shock absorber like no tomorrow.
That's right. And then the second component is NIRIS, which is an infrared camera and also a type of instrument called a spectrograph, which breaks down the light, sort of like when you take sunlight, you put it through a prism and you break it into all the different colors of the rainbow. It does that, but for infrared light, and it lets you really look at like what's going on physically in the objects you're looking at. So through all of these different partnerships, and we have different universities, different people in industry as well, who help us with the engineering side of things, we're all working together. So I don't work for NASA, but I work very closely with our NASA collaborators.
That's fantastic. And you know what? I want to actually just, Florence and Hazel, which, hi, Florence and Hazel, welcome, are wondering, they're 6 and 3, and they're curious, how far into space can we see? And I'm going to add to their question and ask, so we've all had the pleasure of seeing beautiful and astonishing and emotionally evoking images that Hubble has taken. So what is the James Webb Space Telescope going to, what are we going to learn from this when it does get deployed?
So it's hard to talk about how far we can see in the universe, because that sort of implies we know what the shape of the universe is. And the universe is still very, very mysterious. When you ask about big questions like, you know, where does the universe end and what is the shape of the universe? We can't answer that yet. But what we can do is we can try to look as far back into space and also into time, because of the way that astronomy works. When you're looking back in space, you're also looking back in time, because light takes a certain amount of time to travel. So it's sort of like a time machine on top of being an observatory. So Hubble was able to look back into space up to about 500 million years after the Big Bang. So the universe is almost 14 billion years old. So 500 million years after the Big Bang is still very, very early on. But at that point, the first stars and galaxies have already been born. So what James Webb wants to do is look at the birth of those very first stars and galaxies. So by being bigger, it's going to be able to look further back, about 200 million years after the Big Bang. So even further still. So that's really exciting, trying to look back in space and time. So that's one of the things that James Webb will be doing, but lots of other things related to galaxies and also exoplanets.
Absolutely, which I'm very excited to do, to dive into that. Before we do, though, Mr. Sandham's grade 9s, who must be watching together online right now, are curious, is there an optical camera on board the Space Telescope, or is it strictly an infrared telescope? So maybe just talk to us a little bit about those.
Yeah, so that's a really good question. So in terms of instruments that we really use to look out into space, it is only infrared. And we can break down the infrared based on the wavelength of the light that we're looking at. So the electromagnetic spectrum is all the different kinds of light, going from gamma rays and X-rays, which are like really short wavelengths, very energetic, and radio waves, which are very low energy and very long. So visible is like sort of somewhere in the middle. Infrared is a little bit less energetic, longer wavelengths. And so James Webb is concentrating on what we call the near and mid-infrared. So it's the infrared part that's a little bit closer to the visible side. So that is where it's going to be concentrating, and it's going to be working sort of in collaboration with a bunch of different telescopes who look at different parts of the electromagnetic spectrum as well.
Fantastic. In regards to telescope too, you know, seeing seeing your beautiful necklace, seeing the gold honeycomb plates in the clean room, Amy's curious if you can explain the purpose of the honeycomb-like design and why that decision was made and what it allows for.
So we actually see this honeycomb design on some telescopes that are on the ground. We have a telescope in Hawaii. They're actually twin telescopes called Keck 1 and 2, and they belong to the University of California system. And essentially, at some point when you're trying to build a really big telescope, it starts getting really, really difficult to build them in one piece. The mirror becomes so heavy that it sort of collapses under its own weight. And if you know a little bit about how telescopes work, the shape of the mirror can't just be flat, because then when the light comes in, it bounces off and goes back directly in the same direction. So you need it to curve a little bit. So if you try to like build this like one big curved structure that's like huge and heavy, it just sort of collapses. So instead, we start building them into sort of smaller segments. And the honeycomb shape allows for an optimal, like a nice little sweet spot between trying to have no gaps between the different mirror components. Because if we have just a bunch of circles, there's like a bunch of gaps in there where we miss the light, but also being able to like sort of shape the mirror itself by moving the components individually. Because if it was just a bunch of squares, if we start angling the mirror like that, then, you know, there's more light that comes through. But because a honeycomb shape, a hexagon, is like halfway between a square and a circle, it's like a perfect, even like middle ground between those two shapes when you like build a mirror in different pieces.
Okay, I hope that answered, because we did get a couple questions regarding the choice of shape. I also think it's really fantastic. You're talking about, of course, when it's deployed and it unfolds like origami, that origami is something that we can all do at home to understand mathematics, physics, and how we might actually participate in these types of really phenomenal initiatives in all of our own futures. And so they've got some really interesting questions coming in around the birth of stars, nebulas, galaxies, and just really expanding into this, such as that curiosity is what you got into your existing career. And you focus on, you focus a little bit, I believe, on the life cycle of galaxies, don't you?
Yeah, that's right. So galaxies I'm a very visual person. And I think even people who don't work in galaxies will not argue that galaxies tend to give the most gorgeous images. We're getting to the point where like planets, you can start taking nice images and like they're super important and interesting to study. But to me, nothing beats visually like the picture of a beautiful galaxy. So I also remember seeing the Milky Way in our sky the few times that I got to see them out of the city, and it was really striking. So I really fell in love with galaxies, and I study lots of different kinds of galaxies. The spiral galaxy is the most photogenic, so it's probably the one that people know the most. But we have other types. The elliptical galaxy is a little bit more boring, maybe visually, but lots of interesting stuff happens within it. It's usually redder, you don't have the spiral pattern, and they're usually a lot bigger and a lot older as well. But those are the two main types, but there's like lots of different weird galaxies in the middle. Lenticulars are sort of like right in between what a spiral and an elliptical galaxy is, and irregulars are super common, but like just a big mess. They are like really, really hard to study. and my interest is to try to understand all types of galaxies and how they evolve from one type of galaxy to another type. So the way that I like to explain it is, imagine if you are a fly, a mayfly, who can only live for a single day, and you're a really intelligent mayfly in this scenario, and you want to try to figure out, how do elephants work? How do elephants live? And elephants live over 80 years. They're like really long-lived creatures. So what do you do as a mayfly if you want to understand the birth, growth, and death of an elephant? Well, what you want to do is you want to study a herd of elephants that have elephants at all stages of their evolution. And luckily, galaxies tend to live in herds. So they are these huge groups of galaxies that are at all different stages of their evolution. And we know of like 1 trillion galaxies in the known universe. So I have like a huge playground in which to try to figure out how galaxies work. And we can not only like look at all of them individually, but we can actually see how they interact with each other. Because just like with a herd of animals, they won't just be evolving alone, they'll be evolving together. So sometimes you get galaxies that are colliding with each other and galaxies that are merging. So we think that spiral galaxies are probably like babies, and they end up merging and colliding together and forming and shaping a bigger, older elliptical galaxies. So I sort of treat my galaxies like a herd of animals, and I try to like use the mindset of a zoologist trying to understand how they evolve over time.
So really interesting to think about how you have to look at this through multiple perspectives to make it even understandable to yourself, but also how you can communicate it to others. And this gets into the question that Sashkat on YouTube just asked, which was, yeah, do galaxies ever collide or crash together? And you're sharing that that's part of the evolution or growth of galaxies. Sometimes that happens and that transforms into a different phase or combines. And Sashkat is also wondering, will our galaxy ever be on a collision course with another one?
That is a great question. And I can confirm that yes, it will. So we live in a galaxy called the Milky Way. It's a spiral galaxy. We can see the disk when we are just, away from the city. But because we're inside the galaxy, it's hard for us to get like a bird's eye view. It's impossible for us to get a bird's eye view. But we have almost a twin spiral galaxy. It's actually this one here. This is called the Andromeda Galaxy. And we think it looks quite a lot like the Milky Way. It has little galaxies called satellite galaxies that actually orbit it. So you can see one right in the front there and a smaller one in the background there. And so we live in a group, we live in a herd called the local group, not a very original name. And there's about 100 of us in here. And the mama and papa in there are us, the Milky Way, and Andromeda. And we are on a collision course towards each other. So in about 4 billion years, we will merge together. So I actually have an animation here where you can see right now, this is the view of the sky if we were to look tonight. We have the Milky Way, the disk that are streaming across it. And we have sort of a little bit left of the center, a little galaxy, that's Andromeda. And you can see over many billions of years, our night sky will change dramatically as Andromeda gets closer and closer. And when they start merging, you'll see all these bursts of new stars being formed in our sky until after about 4 or 5 billion years, all of the chaos will sort of settle and we will just live in like one single giant elliptical galaxy. So yes, you have that to look forward to in 4 billion years.
Well, see, we talked about really, we are in a mode of time travel, always looking back to understand now. But then to your point, we can look forward because of what we know. In regards, you've been studying, of course, galaxies, which thank you for walking us through this because it also centers us in where we live here on Earth, which is a marvel and so unique. No matter what we learn about potential habitable exoplanets and otherwise, we still center ourselves here on Earth as unique and the place that we as humans can survive and thrive in other living beings. But you do study habitable exoplanets and other and so is this a role that you also think will the James Webb Space Telescope be helping with this search? And what gets you really excited about this? And what should everyone at home know as we continue to hear in the news, Earth-like planet discovered, Earth-like planet discovered? What are the really interesting things that we should know and pay attention to?
Yeah, so the Canadian instrument was actually developed in huge part to try and learn more about exoplanets. So we know that we live in a solar system, we have our own planets, but it's been actually several hundreds of years where scientists have theorized of the existence of other worlds. So we know we have lots of stars in our sky and we orbit one star, the sun, but they thought, well, if this star, the sun, has a bunch of planets around it, why couldn't these other stars have planets around them as well? And it actually took hundreds of years in order for us to gain the technology to actually be able to observe these exoplanets. But in 1995, we were able to observe the first exoplanets. And now 25 years after that, we know of over 4,000 of these worlds. And these are just a few artistic representations of these different worlds. And you can see that some of them are big like Jupiter and gassy. Some of them are smaller. And the smaller ones are sort of very intriguing because we're very interested in finding what we call like an Earth 2.0. I want to mention it's not to move there because they're very far away and we would not be able to move there. Not even one person, even less like the entire human population. But it helps us gain perspective on the uniqueness and the formation of our own Earth and how fragile the conditions are here. So when we want to try to find these Earth-like planets, we are interested in finding rocky planets that can have liquid water. And the way that we define having liquid water potentially, when we can't examine the composition precisely, is to look at planets in the habitable zone or the Goldilocks zone of their star. So you might know Goldilocks goes through the woods and then ends up in a cabin and wants to eat some porridge. One porridge is too hot, one is too cold, and one is just right. So we were looking for these planets that are just right, meaning they're the right distance from their star, the right temperature for there to be liquid water if there is water at all. So that means that if it's colder, it would be ice. If it's warmer, it would be all evaporated. It doesn't mean that there is water. It just means that there could be liquid water. So it's quite difficult, but we know of a few of them now, where we found them using a bunch of different telescopes. But what James Webb will be able to do, which is very, very unique, is it will be able to study these planets as they pass in front of their stars. James Webb will be able to study the light of the star streaming through the atmosphere of the planet and tell us what molecules exist on those planets. And those molecules could be water, they could be oxygen, ozone, and some of those molecules might actually even tell us not only if there's livable conditions, but if there is life there. So we might be able to find alien life with James Webb.
Incredible. And, you know, because I'm so glad that you showed this, because we had a few questions and it was definitely a curiosity of mine too. It's like, how do we look for the conditions for life on other planets? And so you're mentioning like rocky water, you know, the ozone, what the atmosphere is. And so thank you for that, because it just kind of shows the tools that we're able to use and how we can like basically find the hints and clues as we do this. Let's talk though about alien life. This must be, you know, we like to imagine this, and we think about the Fermi paradox. We think about even just like wonderful imaginative stories. What are we looking for when we're thinking about life on other planets, and what do you think about, especially like this being your career and looking at habitable exoplanets, not only because, to your point, highly unlikely we'll ever get there, but what could be there, right?
Mm-hmm. So it's a really tough question, but it's one that I really love to answer, because a lot of the times people think that when we're looking for alien life, they think of listening for radio signals or something like that, and trying to find intelligent life. But when we look at the history of life here on Earth, the Earth is about 4.5 billion years old, and we've had life on Earth for a long time, for about 4 billion of those years. But for the longest time, the life was microscopic, unicellular, very, very basic. And we think that it might have started in like really unusual places, very, very sort of hostile, inhospitable places, like the bottoms of the oceans where you have geothermal vents that have like toxic gases streaming out, but there's heat there. And so bacteria can sort of feed off of those different gases coming out. And so life on Earth is already very wild and complex and a lot different from just humans. Humans are actually very, very fragile. I get uncomfortable when it's like, below zero, even though, I'm a Canadian, I can deal with it, but I get cold. And then, we get really, really hot if it goes above 30 degrees. But there are different forms of life here on Earth that can, withstand much more harsh conditions. So tardigrades or water bears are our favorites to talk about, but different bacteria as well. And so these little guys, they're maybe just a few millimeters wide, and you can see them moving around, just tiny, tiny, and they can withstand really hot temperatures, like 120 degrees or really freezing temperatures. They can withstand nuclear radiation or the radiation of space. So already here, we're starting to be able to sort of broaden what our definition of life is. And so we think it's much more likely for us to find something that is sort of like this. But even that is sort of constrained because we are defining life as we know it here on Earth. So there could be forms of alien life which are totally weird and foreign that we can't even begin to imagine them. But we have to start somewhere.
Within our sandbox of what we know.
Exactly. Right? Yeah. But we have to start somewhere. So we stay inside our box for now, and then maybe we'll end up finding and being able to identify a totally new form of life, which is not unlike anything on Earth.
Well, I think that's a really phenomenal and important role of tools like the James Webb Space Telescope and what Hubble has been able to show us, over the years, and what we have the potential to see as this telescope is launched, is because I think each time we start to get more data and more clues, that sandbox of what we know of as reality or how we view and imagine based on our current data starts to expand or flow into different ways. just before we move on, because I've got some really interesting questions that take us back to the telescope itself, and also a few key questions about galaxies. I have a couple books at home that say there's no life on the moon, and then now I see the tardigrades, and I just think those books need to be updated. Do you know what happened with water bears on the moon?
So tardigrades or water bears have been included in lots of different like space experiments to try to figure out like exactly how resilient are these little guys. And so there was a probe that was sent on the moon about a year ago now, and there was like a little capsule with like a bunch of tardigrades in there. But unfortunately, that moon landing failed, and it sort of like crashed into the side of the moon. So it's just like a whole new experiment where all these water bears are on the surface of the moon now, just doing their own thing. And we're not exactly sure what is happening to them because we haven't had any follow-up observations of them.
Yeah, precisely. So interesting, though. So many books need to be updated. I want to go back because and just find a quick question here. Back to, we've got a couple of classrooms that are engaged right now, and so they're sending questions to their teachers, and their teachers are sending them along to us as well. And so again, we've got some grade 9s that are curious. Specifically, can you share if there's a range limit for spectrography with the James Webb Telescope? It's a really specific question. We've got a curious one. That's great.
Yeah. So the range limit will depend on the instrument. So I don't know if do I have my like super involved? Yeah, there you go. Okay. I've got some extra slides for the like really, really keen people. So there are 4 different instruments, as I mentioned, and almost all of them are a combination of a camera and a spectrograph. And so you have NIRIS, NIRSpec, and NIRCam, which are all going to be looking in the near infrared. And if you're like want to get really into the little details, they go from about 1 to 5 microns, which is the like wavelength of light. And we have one instrument called MIRI, which is looking in the mid infrared. And so that'll be going from about 5 to 30 microns. So we cover a pretty wide range using these 4 different instruments, and they all are going to study slightly different phenomena because different phenomena in space will shine at slightly different wavelengths. So it's important to cover the entire range of wavelengths.
What types of teams will be observing this data as it comes in, and what will they be looking for specifically, and what are you most excited about that could be discovered or shared because of this?
So that's a great question. And obviously we want to be involved in James Webb because it's a worthwhile effort, but we also get some time on the telescope guaranteed as Canadians in return for the contribution that we made. So because we gave one instrument, we have a few hundred hours on the telescope during the first year or so that have already been assigned to different groups that have worked on the telescope itself. And there are different projects, really interesting projects, some that are observing super, super old galaxies, some that are observing like Earth-like planets who are trying to find potentially alien life or life Earth-like conditions. And so we have a lot of time. And beyond that, even how telescopes usually work is that a bunch of different scientists team up together. They do a group project essentially, and they write a proposal saying, this is what I want to do with the telescope. This is the part of the telescope I want to use. And this is what I want to look at. And this is why what I want to look at is really, really cool. And you should give me the time. And then there's like an internal competition, and then time is awarded that way. So it's very, very open, actually. And some of the time is reserved for the people who worked on the telescope. But beyond that, it's completely merit-based. Any astronomer in the world can apply for time on James Webb because we want the entire community to be able to profit from it. So lots of different fields and coming from lots of different scientists from all over the world.
I think it's really powerful in being reminded of that. And then the global access and global findings and global sharing is that looking up into space, although kind of really feeling like this competitive push, actually brings a lot of us together, community-wise, culture-wise, country-wise. And so it's nice to be reminded that in a massive and important project like the launch of the James Webb Space Telescope, that there's global connectivity and transparency and access and that what you're working towards is going to be accessible and viewable for others to help us all discover new things.
Mm-hmm.
I want to take us into a couple of really fantastic questions. So we're going to ping pong around a little bit, which is great. Atticus has a really great question, wondering, is it possible for a planet to have an elliptical orbit that would go through a habitable zone, too hot and too cold? And what would happen if that were actually the case? I love this question.
So yeah, that is a great question, and one that I have never had before. I've been doing this for about a dozen years, and it's rare for me to get like a brand new question. So yeah, definitely there are planets that have elliptical orbits. We have some dwarf planets that have elliptical orbits in our own solar system. Pluto has a very elliptical orbit. It actually comes inside of Neptune's orbit for part of its journey around the sun. But it is possible for planets in general to have elliptical orbits. In the case of something that's sort of like going in and out of a habitable zone, that would mean that if there is life form on it, it would have to adapt to those sort of like seasons. And a lot of things would depend on like how far out it goes outside of the habitable zone. Depending on its atmosphere, an atmosphere can actually work wonders in sort of stabilizing temperatures, which we can actually see here on Earth. So we don't get sunlight for about half of the day, which is nighttime, and then we get sunlight for the other half. But there aren't like a huge difference between nighttime temperatures and daytime temperatures because the atmosphere is sort of stabilizing everything. So a thick enough atmosphere could stabilize that as well. But even beyond having an elliptical orbit, sometimes you can have really weird things like what we call tidal locking going on in some of these planets. And it's the same phenomenon that we see with the moon. The moon always shows us the same side. There's a dark side, but it's not actually always dark. It's just that we never see it because it always has the same side facing the Earth. The same thing can happen with some of these exoplanets where always the same side is facing the star. So there's like a side that's always really bright, one side that's never bright. And we think in those cases, perhaps where there is a chance to have life is right on the terminator, which is like the line where between daytime and nighttime, where there can be more of a mixing of temperatures because of an atmosphere. So maybe in those places, the only places there can be life is like right on that line, like a ring of life around it. So depending on the different orbits and the different orientations of these planets, you could probably get some like pretty wild results.
See, that's fantastic. So interesting. There was a question a little bit earlier, and I'm sorry that I can't quite remember the name, but the interesting thing that all of us grounded here on Earth often like to imagine is what actual human space travel could encompass and where we should go. And there's always an interesting debate about Venus versus Mars. And I'm curious if you would weigh in on which one you think. Is our eye being set on Mars the best, or would you be the one that would vote for Venus?
So I would love to go on another planet, but I don't know if trying to put settlements of people on another planet in general is a good idea. The like romantic and curious explorer in me would never turn down going on another planet. But a lot of what we can do can be done with robots. So I don't know if there should be as much emphasis on like human space exploration as there is. But to come back to your actual question of Venus versus Mars, I would definitely go for Mars. Venus is really intense. The atmosphere is 90 times thicker than it is on Earth. It rains sulfuric acid. So that seems like a problem. Whereas, and we can actually see it because when we send rovers on Venus, they can maybe last a few hours before their internal components melt. Whereas we've had rovers, some really fantastic stories on Mars, Opportunity and Curiosity, who have lived for years and years and years, just like rolling around, taking selfies and taking samples. So already when we look at the lifetime of rovers, when we send them on these different planets, Mars seems much more friendly to us visiting it.
Truth. Absolutely. We have a few minutes left with you, Nathalie, and as we do, thank you for this, because I think that we could spend an entire day and night with you and ask a ton of questions and look at a ton of really powerful images with you. But in the few moments that we have left, Loic is curious about this, and someone else a little bit earlier who was studying astrobiology was curious about this too. For those of us that are interested and want to learn more, what resources should we keep our eyes on? Yes, we can follow science news, but where do we go to learn and just soak this in? So potentially we could take a path similar to you.
Yeah. So online, the resources are really fantastic. NASA is just a gold mine of a bunch of different, not only like sort of scientific news and articles, but they have like really great activities that you can do if you're a parent who would like to incorporate more astronomy into your activities at home. They have things that you can do at home. They don't all require telescopes either. Things that you can use to teach physical concepts to your children. The Canadian Space Agency also has a bunch of different resources. And they actually just put up a new section on the Webb telescope, which I helped write, and a new section on astronomy as well. So I'm helping them develop their astronomy section where you can learn everything about our solar system, and then we'll be incorporating exoplanets and galaxies. And one thing that has changed a lot since maybe I was much younger, Wikipedia is actually very, very solid. It used to like be a little bit less trusted, but in general, I can fall into a Wikipedia hole and just keep reading Wikipedia articles forever. But also, if you're really interested in astronomy specifically and want to sort of like get your hands dirty, there are so many great resources at amateur astronomy clubs who often they love having younger members joining them. It tends to be a little bit older, but they are like ready to like waive their membership fees for younger members, and they know way more about constellations than professional astronomers. And your science center and planetarium is also a really, really great resource. So there's like lots to learn and lots of different places you can do that learning. You just have to go out there and bring your passion and curiosity.
100%. And I think that's like practicing and learning with purpose. If you're curious, you keep an eye on that, eye on the prize, and just keep on digging. And that's also why we're here, and that's why you're here. So thank you so much for that. And then final question before we embark and continue on with our days. What are some really interesting and must not miss astronomical events and things like the launch of this that we should be keeping an eye on and marking in our calendars?
So what's coming up, which comes up every single summer, but is also beautiful, always beautiful, are the Perseids meteor shower, which are peaking August 12th this year. And so if you have the chance, they're really beautiful, and they're not necessarily always the strongest meteor shower, but at least they're in August, not in December. So you can go outside and not freeze. So that's really wonderful. We have a total solar eclipse, not here, unfortunately, but in the Southern Hemisphere, which I was supposed to go and watch with my own eyes, but with the situation, I might not be able to travel to, unfortunately. But there will be live streams of that happening, and that's really wonderful. James Webb will likely be launched in 2021. We don't know exactly when yet, just because there's a bunch of delays, just like with other missions in general. But really, in the next year or so, there's lots of different things coming up. So Perseids are coming up next, and so if you have the chance, I encourage you to go out and look at some shooting stars.
Well, I can commit for those that are here in Southern Alberta that we will do our best to share maps of really fantastic viewing places and even just dark sky territory in Alberta in general, because I think what everyone should experience in their lifetime is something that, Nathalie, you talked about when we first got started, and that's that moment of stepping outside of a community with light pollution and into a dark sky environment. And anyone that's unzipped the door of a tent and walked out in the middle of the night, maybe for other reasons, the call of nature, looks up, and it is astounding and grounding and makes us feel small. But I think, to your point, makes us realize how fragile we are and how beautiful our planet is. And this is our home, and we are each other's neighbors. And it's on all of us to stay connected and take care of each other and share, right? And share in our journey and help one another achieve.
The sky is something that we all share. So we're all looking at the same sky, and it actually makes me feel very connected to everyone and also the universe itself.
Absolutely. And thank you for bringing that sky and that universe to us. We're really grateful. And thanks to all of you at home. There was more questions than we could get to. If there's a couple here, I'll make sure, maybe Nathalie, I'll send you a little note afterwards. And if there's a few little things, we can provide a little FAQ as a follow-up, likely on our Facebook page. And Nathalie mentioned next week, we are talking about volcanoes. And so we're incorporating with a couple of team members from Hawaii, and we're bringing the life of volcanoes and volcano studies to you at home again. And so thank you for joining us. Thanks for giving us your Thursday versus your Wednesday. And we look forward to seeing you all soon. And in science and hope we trust. And I look forward to seeing you in person, Nathalie. The screen has been lovely, but it'd be great to have you here with us soon enough.
I agree.
Fantastic. Thanks, everybody.
Bye.
Goodbye.